In today's lecture, we will learn a very basic, a very handy thing for us, actually. I told you last time that we have binary type of variables, either zeros or ones, right? And I also told you that those variables are really helpful in representing many realistic situations, okay? Today we will actually start doing that. The example that I'm going to use for explaining those is the project selection, okay? Let's read the problem first. We're a manager, and we're trying to decide which projects we should finance, all right? So we have 10 projects ahead of us, coming from different departments, all right? And as a manager, you're supposed to decide which ones you should go for it and which ones you should not, okay? Seems like an easy problem, right? There are 10 projects, you choose among them. Okay, according to what? Of course, each project has a cost, according to this setting. Each project has a profit for us, right? And we have a total budget. So, living in our budget, we're gonna select the most profitable combination of those projects. Okay? If we didn't have anything else, so we're maximizing our profit, we have to remain in our budget, what does it look like? We either do the project or not. What does this problem look like? I can't hear you. We have binary variables, yes. We're going to do this or not. But we have seen this problem on Monday. What was it? You have a budget. You either do it or not. Everything you put comes with its own something. Knapsack, very good. It's exactly like knapsack. If we didn't have any additional requirements, my budget is my knapsack. The cost of each project is the volume of each book. And if I put it in my bag or not is my decision, right? So that's why I told you these problems, well, in the abstract level, they're all the same. They all go to the same kind of mathematical model. Xj, if the thing is in the knapsack or not, Xj is 1 if the project is chosen or not, yeah? Okay. But this time, we have extra additional things coming on. For example, projects 3 and 4 cannot be chosen together. Either they're coming from the same department, or in the knapsack case, one is the book and the other one is the other book, and you don't have the same class at the same day, whatever. You cannot do 2 of them together. If this is the case, how shall we proceed? So, first of all, we're going to model our basic structure, like the knapsack version, right? So what is the decision variable? What is the correct decision variable here? You already said that. Our decision variable is? Binary variable, which takes on the value 1 when we choose the project. So our xj, okay, I was doing it like this, right? All right, our xj is 1 if we choose the project, and it's 0 if we don't choose the project. All right, with this, we maximize our total profit, our objective function, and our, sorry, hopefully I will recover one day. And our budget constraint, knapsack constraint, is this. Each project, if I choose the project, it comes with a cost, and their sum should not be more than my total budget. Okay, this together with xj binary is my knapsack. But now remember, we have many other things going on. Requirement from 1 to 10. So step by step, we will write constraints so that we represent all our environment in our selection process. This time our environment has many things. You cannot choose 3 and 4 together. All right, what else? If you choose, you have to choose exactly 3 projects. Okay, what else? If you choose project 2, then you have to choose project 1 too. What else? Project 1 is selected, then 3 cannot be selected. Okay, what else? 1 or 2 chosen, but not both. All right, so you see, we have many things going on. And this is just a quick example for representing these type of situations. Right? That's going to happen. Like the last 2 are kind of have more general meanings too. I'll come to them one at a time. All right? So let's see. It says if projects 3 and 4 cannot be chosen together. Any ideas how to do that? Yes?
X3 plus X4 is more than 1.
Smaller than or equal to. You always have to have equality. But yes, if we write x3 plus x4 less than or equal to 1, then in the model, in the optimization, there's some cannot be more than 1. There's some can be 1. There's some can be 0. In representing these things, we have to be careful not putting additional requirements, all right? It doesn't say you have to choose one of them exactly. It only says you cannot choose 2 of them together. And this is what's been done by this constraint, right? If you just write this, that they both cannot be 1. That's all I'm trying to eliminate only. And this constraint eliminates that situation. Clear? Any questions? Well, from 1 to 10, we're going to make it more challenging and challenging, all right? This was easier version. All right. Oh, this is also easy. It says exactly 3 projects. How would you do that? Make sure that at the end, your optimization selects 3 projects, exactly. How would you do that? Yes? Exactly. You just sum them up. x1 plus x2 plus x3, and says equals to 3. Because that's what the statement asks for it. So let's write the mathematical representation of it, yeah? Clear? This is interesting. If you choose project 2, you also have to choose project 1. That's what it says. If project 2 is chosen, then so is project 1. Yeah?
X1 plus X2 must be equal to 2.
No, or 0. Because if you don't choose project 1 or 2, then there is no restriction, all right? So you have to be careful, yes?
X1 greater than or equal to X2.
Exactly. Let's look at this. What is the statement says? If project 2 is chosen, so is project 1. So if x2 is 1, x1 is forced to be 1 with this constraint. If x2 is 0, I don't care what happens. And there is no restriction for that anyway. If I don't choose x2, I can still choose x1. There is nothing in the statement saying that I can't do that. All right? In these in these representations, you have to be very careful by just doing what it says only, nothing more. All right? So if x2 is 1, this constraint forces x1 to be 1. I don't know what's happening when x2 is 0, and I don't care. Clear? Any questions? Requirement 4. If you choose 1, you cannot choose 3. How would you do that? Let's think for a while. If you choose 1, you cannot choose 3. So you have to write a constraint saying that if x1 is 1, x3 should be forced to 0. You have a suggestion, you have a suggestion. Anybody else? Come to class, everyone. If you choose 1, so if 1 is 1, 3 should be 0. Okay, I was hearing 3. I saw 3 hands, right? So 4. 5, a new face. All right, what is your suggestion? That is what it goes to, exactly. Because what I want, if x1 is 1, look at the constraint, x3 is forced to be 0. Yeah? That's what I want. If x1 is 0, x3 can be anything. But if x1 is 1, x3 has to be 0. All right. How about this one? Either 1 or 2 is chosen, but not both. Yes? Exactly. You cannot choose 2, and you have to choose at least 1. Either one of them is chosen. You choose either 1 or 2, but you cannot choose both. That's what it says. Yeah? This is a nice one. You either choose both of them, 1 and 5, or you choose neither of them. There are 2 projects, x1 and x5. You either want both of them, or you don't have any. Okay, you have a suggestion. You got the hint of it. How else? There's a new face, yes? x1 equals to x5. That is what it says. If you choose 1, you're choosing the other one too. If you're not choosing one, you're not choosing the other one. Their values should be equal to each other. x1 plus x1 equals to x5. Clear? Got it, right? I'm not going too fast, I hope. Okay, how about this one? At least 2, and at most 4 from this set should be chosen. At least 2, and at most 4. I want new faces. Yeah, you haven't talked today, yeah. Now, this is easy, because some number can be less than 4 and greater than 2. So what this says is you want the summation of this set. The projects chosen from this set should be equal to 2, 3, or 4, right? We'll come to challenging versions of those two, but this one, the intersection is not empty, so it's doable. You just sum them up, and you want that sum to be at least 2 and at most 4, right? Clear? How about this one? Let's read it together. Neither project 5 nor 6 can be chosen unless either 3 or 4 is chosen. Hold on, what is it saying, right? Let's read it again. Neither 5 nor can, neither 5 nor 6 can be chosen. So you cannot choose 5 and 6 if you haven't chosen 3 or 4. If you have chosen 3, you can choose both. If you have chosen 4, again, you could choose both or none. But you cannot choose them if 3 and 4 altogether 0. That is the trick in here. I want you to think about it a little bit, because this is a little bit challenging. x3 plus x4 must be bigger than what?
x5 plus x6.
Plus x6, is she correct? So let me write what you have just said. You're saying that x3 plus x4 is, say it again. Is this what you're saying? Okay, let's discuss this constraint together. Is this correct or not? Now, yeah, what do you say? Exactly. You're not letting both of them to be 1 when one of these is 1. You're forcing both of them to 0 when both are 0, fine. That is one thing that you have to do. But you also have to let them, you have to allow that this thingy, both of them can be true, right? Now this is what I have. So this says if their sum is 0, then both of them should be 0. This is satisfied with this constraint. But if you do it like this, it's correct. Because her version does not include the case that they're both can be 1. Got it? You could have fixed it like this though. The one on the right. If you have written 3 to 2 in here, then it would be correct, your version. Yeah? Did we all get it? Now our life is a little bit harder. It's not that easy to do these things. Let's convince ourselves together. Let's read the statement. At least 2 of 1, 2, 3 are chosen, or at most 3 of those are chosen. If it was and, it's easy, yeah? You write both of them. You want x1 plus x2 plus x3 greater than or equal to 2, and you want 4, 5, 6, 7, 8 less than or equal to 3. All right. But it's not and, it's or. So we have to model the situation where either this or the other one is true. Got it? Now, first convince yourselves that this number 9 cannot be done like the ones we did up until now. We can't say their sum is greater than 2 and plus whatever. This requires a little bit more trick. We want to ensure that at least one of 1 and 2 is satisfied, because that's what it says. You either do this or the other one. You can do both, but it's not a requirement. You have to tell the model that you're doing or. All right? So we cannot write and. If we write and, we're solving a different problem. We have to write it in the correct form, which is or version. Did you all get the problem? Okay. This is a general situation. We call these either or constraints, okay? And this happens a lot in real life. Either this or that should happen. It happens a lot. So how we handle this is, I'll give you the path for general version. So depending on your f function, you can immediately come up with the correct way of doing it. So say we have 2 constraints, f of x less than or equal to 1 and g of x less than or equal to 2. And your environment says either one of them should be 1, should hold. You have to make sure that at least one of them is holding in your constraint set. It's okay to have both, but you don't have to. All right, that's the most important part. We want to make sure that at least 1 and 2 is satisfied, and these are called either or constraints. All right. How do we do that? We define another binary variable. The binary variable will just take care of the fact that the constraint is satisfied or not. Right? So I define a y, a new binary variable. It has nothing to do with my projects, nothing with my knapsack, nothing related with my decisions, original decisions. It's an additional binary variable. We just use it because we need it. We just use it to represent this either or situation. Okay? So this is what I write. f of x less than or equal to m. M is a large enough number. Because when we don't want to hand in the situation like it happened before. If we want to have some big number there, we should allow the model to take on that big number. So we just multiply it with a large enough number, whatever it is, right? Then if y is 1, okay, your second constraint is satisfied. This one is satisfied when y is 1. When y is 1, this thing becomes 0. And your gx less than or equal to 0 is satisfied. Y is 1, this can be satisfied or not. Depends on the optimization. I'm not putting an additional bound, but I'm sure that gx is less than or equal to 0 when y is 1. All right? If y is 0, then this thing is satisfied when y is 0. This thing can be satisfied or not, I don't care. But I know that fx is less than or equal to 0. And y will be 0 or 1 anyway. So depending on the value of 1, my optimization model will choose which constraints should be satisfied and which one should be or not, depends on the other things going on in my optimization model. Got it? This is how we actually represent it. So when you put y equals to 0, the first constraint becomes active. We say it like that. And condition 1 is satisfied. I don't know what's happening to condition 2, but I don't care. And if y is 1, then second condition is satisfied. And the first condition just becomes is bounded by a large enough number. So you have to be careful, by the way, that this number here is large enough. All right? Like in our previous case, if this is the summation of the projects, you should have at least 10. Well, you should have 10. 10 is safe there. Because there's some cannot be more than 10 anyway. Yeah? So that large enough number should be large enough. But of course, in order to make the solution easier, we also make it as small as possible. Right? So, okay, 10 is safe. But how about 9? How about 8? It's going to depend on my f function in here, and we're going to derive what that m should be. Because you have to tell the optimization. You cannot leave it like that. You have to give a number while giving it to the optimization model. So, my either-or constraints. Either this or this should be satisfied. So I define another binary variable, which is 0, 1, and multiply my constraints with a large enough number of that variable so that my conditions are satisfied. Is it clear? Now I'm going to drive the m. If we are okay with m being large enough, these two conditions actually satisfies my either or, then I'm going to drive what m should be. Questions? No? Good. Then, let's come back to our example. It was saying that at least 2 from here and at most 3 from here. So this is my condition 1, this is my condition 2. But the path I've shown to you was using fx less than or equal to 0 and gx less than or equal to 0, right? Let's convert them to that version. So this thingy becomes this. This is fx less than or equal to 0. And this is my gx less than or equal to 0. Yeah, I just converted them so that they look like less than or equal to 0 version. Clear? All right. Next. Anything I do it here appears here too. That's fancy. Okay. Then problem becomes, what should m be? I can't leave it like m. I have to make sure that there is a number there. I told you those m's represent like, okay, let's look at the first constraint. 2 minus something's less than or equal to m times y. Yeah? Here it is. Oh, here I have shown you that m equals to 2 will be enough. Putting m equal to 2 will be enough. Why? Let's see. If m was equal to 2, my constraints will look like this. Yeah? Okay, when y is 1, what's happening? When y is 1, oh, okay, let's do it here. Because when y is 1, the first constraint says their sum should be greater than or equal to 2. Is it? When y is 1, what's happening? Which one is active when y is 1? Second one. When y is 1, the first constraint says their sum should be at least 0. Well, their sum is at least 0 anyway, right? But if this was something else, it would be a problem. I couldn't have like 5 there. Okay. The second constraint says if y is 1, their sum is at least 3. That's because it becomes 5 when I put m equals to 2 there. Yeah? When I put m equals to 2 and I rearrange the term, this one becomes like this, 5 minus 2y. Okay, so when y is 1, this becomes active. When y is 0, what's happening? When y is 0, which constraint is active? Çok yaşa. The first one is active when y is 0. What's happening to the second one? The second one says their sum should not be more than 5. Is it correct? Can their sum be more than 5? No. If it was 4, it was a mistake. Then your m was not large enough. This is what I'm saying. Their sum can never be more than 5 anyway. Okay then. So putting m equals to 2 in here and rearranging to convert them in here is working. That's what I'm trying to show you. Clear? Yes. Can I repeat? Yes, I can. You want me to repeat to the proof that m equals to 2 works? All right. Now, everybody is with me in here, right? Everybody is with me when I convert it to this version, the one in here, right? Okay. Now, the question is, what is that m? I can't leave it like m. I have to tell the model. Remember the certainty assumption, all right? I should give something to my optimization solver. Otherwise, I'm stuck. Yeah? Okay. M should be large enough. So all you need to be careful about is when these constraints become active and inactive for one y value. For the other y value that the constraint is not active, I shouldn't put an additional restriction there. Okay? So let's see. When y equals to 2, I rearrange. When m equals to 2, you rearrange and you come up with this, right? And if you do that, what's happening? Let's see. When y is 1, I put y equals to 1. The first constraint says their sum is greater than or equal to 0. Fine. Their sum is always greater than or equal to 0. No problem. So check in one problem should say no problem in the other version, right? When y is 0, the first constraint says, okay, my condition 1 is satisfied. How about the second constraint? The second constraint says their sum cannot be more than 5. Yeah, their sum cannot be more than 5. So the m you put there should work okay for the case when the constraint is not required. So when y equals to 1, this is active. Then in that case, the one on top should be okay. When y equals to 0, this is active. In that case, this one should say okay, no problem. All right? So your m's should satisfy that condition. Clear now? Yes. Thank you for asking this question. Now, it's not easy to come up with challenging questions, all right? So when we're asking these kinds of questions, I want you to represent each requirement separately. So now in your mind, you're actually solving. And okay, the constraint 2 is also, the condition 2 implies 5, so don't do that, okay? treat each one of them separately because I'm just trying to show you how to represent those conditions. But if not said so, yes, you're right. Okay? He said because we had a condition saying that choose at exactly 3 from all set, and this one is actually, sometimes the conditions I have written in the question may even conflict with each other. It's okay. Just represent them individual from each other, independent from each other. Okay? Is either or correct, understood? You're going to do it a lot. Okay? Okay, this is a different thing then. If we're done with either or, I'm switching to another requirement, the last requirement. All right. The last requirement was saying that if both 1 and 2 is chosen, then at least one of 9 and 10 should be chosen. What does it mean? If both 1 and 2 is chosen, if their sum is 2, then at least one from 9 and 10 should be chosen. If this is 2, their sum should be greater than or equal to 1. There's a reason this is the last requirement. You have a suggestion? Yeah. All right, let's do that. No worry, but I'll open my Blackboard. Hold on. X1
bigger than or equal to, in the parentheses of 2, x9 and x10.
Let's discuss, is this correct or not? If both are chosen, yeah, he already figured why it's not correct. It says, if this is 2, I want this to be greater than or equal to 1. This is not working right now. This is not doing what it's supposed to do. Okay? And I have to write a linear constraint for that, right? Because we're in LP domain. How do we do that? Well, the requirement 9 was an example for a general situation that we refer as either or. And requirement 10 is what we call if then. If this is happening, then this should also happen. If this is not happening, I don't know. And I don't care, again. All right? So if this is happening, then I have to make sure that this is also happening. If then. Again, they have, I'll again show you a path to do that. And how we represent this is we're going to utilize Boolean logic and convert this if-then requirement to either-or requirement and use the same trick that we used in either-or requirement. How do I do that? Let me walk you through. So the constraint says, the requirement says, if a constraint, this time I'm using strictly greater than or equal, greater than, because I need that. So if fx is strictly positive, then gx should be less than or equal to 0. I have to convert it to this form so that I go to either or. Now, if the if statement, if it is not satisfied, I don't know what's happening. But if it is satisfied, I have to make sure that the other one is also holding. All right? This is what it is. So we want to ensure that if fx is strictly positive, then gx is less than or equal to 0. All right? How do we do it in either or format? Well, this is actually this. If fx is less than or equal to 0, so we either have this or that. Because if the other way is true, I have to have this. Remember our either or? It was saying it's either this or that. Now, if one is not satisfied, one not satisfied means that my f thingy is strictly positive. Then 2 must be satisfied. This is what we were doing in either or, right? Either 1 or 2 must be satisfied. Now, if I convert my if-then statement to this version, now I know what to do, right? Did you get it? This is again a trick. A handy trick that you can use in many real situations too. All right? So what I did is, I actually converted this if-then requirement to either or. Now I know how to handle this. I'll do my, m times 1 minus y, and I'll define an m for that. I'll find a large enough m, and I'll be done, yeah? Got it? This time you have to represent your if statement as strictly greater than statement less than or equal to. Then it becomes like this, because this is how I want in the either or type of statement. These will be my constraints in my LP, and that's why it works. Got it? Questions? I'm not seeing nods. Did you get it or not? You want to see the constraints. All right, let's go. So this is the either or version of my if then. So my if then was if f positive, then g less than or equal to 0. Yeah? So if this is true, then this is equivalent to either or version. And here is what I used to do with the either or version, right? I define a binary variable, and I represent one of them with z and the other one with 1 minus z. Yeah? This is how we handle the either ors. Then I find the correct m for this. Let's look at our formulation, our requirement. It was saying that if both 1 and 2 are chosen, then at least 9 and 10. One from 9 and 10 should be chosen. What it is, so this is my fx, and this is my gx. But I have to be careful, yeah? I want fx to be strictly positive. So how do I write this? Their sum equals to 0, means their sum is strictly greater than 1. Because I need a strictly inequality there. And the last one is x9 plus x10 greater than or equal to 1. It's in the correct form anyway. So this is my f, and this is my g, yeah? I want x1 plus x2 minus 1 strictly positive, then 1 minus x9 plus x10 less than or equal to 0. So this is f, and this is g, yeah? All right? Either or version is this. So either this or this should be satisfied. What does it mean if this is not satisfied? This is not satisfied means that their sum is strictly greater than 1. While their sum strictly greater than 1 means that their sum is equal to 2, then this thing should be satisfied, which is what I want, which is my requirement. Yeah? So you do the math, fx, 1 minus z, gx, m times 1 minus z, and here in this version, m being 1 is also enough, and you just put m equals to 1. This is what happens. If z equals to 1, or if this is 2, that means z equals to 1, and if z equals to 1, 9 plus 10 is equal to greater than or equal to 1. So if this is 2, I'm forcing 9 and 10 to be greater than or equal to 1. If their sum is 0, I don't care what's happening. That variable actually, it was y in the either or case. It's the same thing. It's an additional binary variable that we just define to handle this either or situation. So in real life, it means nothing. It has nothing to do with my project selection. It just helps me, helps me to represent my real life into mathematics. So it tells me at the end which of those constraints is actually satisfied. Because that was a requirement for me, I have to make sure that either this or that is satisfied, and z being 1 or 0 tells me which constraint is satisfied. Now, so this is our whole model. Even though I told you the conditions are independent from each other, because my second constraint and my, less than or equal to 3 constraint may not work together, but normally, if everything has to be taken care of together with the knapsack version, you have to add them all together, right? And be careful, you cannot use the same binary in 9 and 10 if you're using it together, right? Because for us, y was representing which, why is it not working? For us, y was actually representing which of these two conditions are satisfied, and z is representing which of these two conditions are satisfied. Also your m's, okay? You have to be careful what you're using, and one of them should not, usually does not go to the other one. How do we find m? Now what you're supposed to do is you look at your constraints. Now in here and in here. This whole thing, and this is, we're putting an upper bound, right? So we have to make sure that, and this condition was working, this one was working when y equals to 1. So when y equals to 1, I have to get a 3 in here. And when y equals to 0, what I got in here shouldn't be a bound. Okay? So this is like 10 minus 2y is also correct there. But 5 is the smallest large enough number there. All right? And on the upper part, when y equals to 0, this condition should be satisfied. I want it to be 2. And my m was actually m times 1 minus z. So that could give you a trick. Usually, the less than or equal to m gives, but usually, it's not always. You have to play and you have to prove yourself, all right? But usually, this lower bound gives you a hint in figuring the correct m, but you have to write them and choose that it really works. Convince yourselves that it really works, okay? For example, I cannot put 3 in here because I don't want that. I want their sum to be greater or equal to 2. Yes? You didn't understand what? How to find m. Okay, I cannot tell you that, I cannot immediately give you the m. What I do in finding m is because, hold on, let me go back all the way through. Yeah, there it is. It is either mz and n times 1 minus z, right? So what I do is, I put z equals 0 and 1 with the m versions. I rearrange my terms because there's a 1 in here, 1 in there. Yeah, I write the clear form. Then I see what I need next to that.
But why in the previous discussion, why did we set m was equal to 2?
Because m2 was working. What do I need? Well, I need this thing to be greater or equal to 2 when y is 0. When y is 0, this was m times 1 minus y. When y is 0, this thing is greater or equal to 2. No, because that's not my either statement. My either or was saying that this is greater or equal to 2, and their sum is less than or equal to something. And when you put 1, it's not going to work in here too. That's why. So again, what I do, I look at the things, I write it in the form of m first. Here it is. I write it in the form of m. I rearrange. I see what I see next to y, multiplied, like y is multiplied with something, m plus some number, I don't know, and 1 minus y is multiplied with something else. Then I look what I want in my constraint, in my requirement. I was requiring greater than or equal to 2 and less than or equal to 3, if I'm not mistaken. So I want to make sure that I'm satisfying this with the m versions. It may look like, because you haven't tried it on your own, just try it on your own. This either or and if then statements, try that for the first one. First of all, it's the smallest large enough number, all right? So probably m equals 3, 4, 5 is gonna work for the first either or requirement. Try it on your own, see that it works. But then also see that 2 is also working. Okay? Yes, but I would be asking, find the smallest such m. And if 8 is correct, and if you found 9, 9 would be correct, but it wouldn't be the smallest such thing. Because in 303, you would be starting solving these problems. And in solving those problems, these are actually bounds. And you want those bounds as small as possible for the solution purposes. Any other questions? Again, I repeat, try to find M's. Convince yourself that which M works, which not, on your own, on a piece of paper. And do it as soon as possible, because your next homework is coming today, which will definitely use all these tricks that I'm teaching today. Let's have a 10-minute break. We'll continue in the next hour.